Assalamu alaikum everyone. My name is Ahmad Sabri Rajab. We are Group 3. I will be present the introduction part for our experiment 6 torsion of the bar. So we should know that the torsion bar is where the rod or bar that resists twisting and have a strong tendency to return to its original position. For example, in the automobiles, a torsion bar is a long spring steel element with one side end held rigidly to the frame, while the other and twisted by the lever connected to the axle. It thus provides a spring action for the vehicles. So for our objectives for this experiment, the first goal we want to achieve is to investigate the relationship between torque and the angle of the twist. The second objectives to determine the models of rigidity of the materials. Okay, so for the theory part, we have an equation which is L gamma equal to B theta. Then the gamma will equal to B theta over L. Here we can know what is the gamma and what is the theta. So for gamma it is the shearing strain, theta angle of the twist, L the length of the shift, and P the length from the center to any point in the circle of the shift. So this image can show that the shearing strain gamma is measured by change angles formed by the sides of that elements. So for the shearing strain is maximum on the surface of the shaft, B equals to C, and the gamma max will equal to C theta over L, where the gamma max is the maximum shearing strain. For the C it's the radius of the shift, theta the angle of the twist, and L the length of the shift. For the elastic range, yield stress is not accessed anywhere in the shaft where the Hooke's law applies, and gamma max will equal to Tc over Jg. Then the theta will equal TLJg, where the T is the torque, G polar moment of inertia, theta the angle of the twist, and L the length of the shift, and for G it's the modulus of rigidity.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Adil Lukman Biazali. I am from Group 3. Today I will present the methodology for experiment 6, which is torsion of bar. For this experiment, the name of apparatus, which is we use three type of solid bar, which is nylon, steel, and aluminium. We have a ruler to calculate the distance and digital caliper to calculate the diameter. We use a load which is 1 Newton, 5 Newton, and 10 Newton. And 5 we have a hanger. For procedure, firstly we use the nylon solid rod and clamp it fits at the fixed clamp. For this picture, we fix like this, and next step up the length between fit clamp and rotation scale, which is shaft at 5 cm. We use a ruler to calculate the distance for 15 cm, and next hanging the load hanger to the rope, this picture, and make sure the reading of the rotation angle is 0, and hanging the load start to take the reading and follow the table from this picture. Next, take the reading rotation angle for vary value for the load. And next, repeat the step 1 until 5, which is different length of shaft, which is 30 cm for the same type of rod, which is nylon. Repeat the step 1 until step 6, which the different type of rod, which are 3 steel and aluminum. Calculate the value of torque for the both of the different shaft length and draw the graph between the value of rotation angle again the value of torque T. Next, the last, measure the diameter of solid rod and the torque by using the digital caliper. For this picture, we use digital caliper to calculate the diameter of the rod, and the next picture SM. That's all from me. Thank you.
Hello, my name is Noratika Shahira binti Uyuk. Now I will present about the result and calculation for this experiment. First we measure the diameter torsion head efficient, which is we get 68.34 millimeter. From that we calculate the radius, which is equals to 34.17 millimeter. From the radius we use the formula of torque, which is torque equals to R times F. F is the force, which is weight of the load that we use. For this experiment, we need to calculate the modulus of rigidity. To get the modulus of rigidity, we use the calculate of the twist of angles equals to torque times length divided with J times G. So from that we need to read from the graph, which is the value of slope. The value of slope is equals to twist of angle divided with torque. So from that we can get the modulus of rigidity value, which is G equals to length divided with value of slope times with the moment of inertia, which is J. So from that we need to calculate for the all type rod that we use. So firstly, this is the table for the nylon rod and the graph for nylon rod. So from the table you can see all the data that we get from our experiment last week. So we measure the diameter nylon rod, which is 6.62 millimeter, and the C equals to 3.31 millimeter. C we use to calculate the moment of inertia after this. For the nylon rod, we use the weight load in Newton, which is 0, 2, 4, 6, 8, and 10 Newton. So from the weight, we use to calculate the reading of twist angle for different length. We have two different length, which is 50 centimeter and 30 centimeter. So after we get all the reading of the twist angle, we calculate the torque for different length, which is for different length, even the different length we get the same torque value because we use the formula that I have explained just now, T equals to Fr. So as you can see, the nylon rod have a graph which is twist angle against the torque, and as you can see, the trend line that we get, which is for the red line is for length 50 centimeter, and the blue trend line is for the length 30 centimeter. From this trend line we get the value of slope, which is 0.1217, and for 50 centimeter we got value of slope 0.0619. So next, show the table and the graph for the steel rod. So we use the diameter steel rod, which is equal to 5.10 millimeter, and the C is equal to 2.55 millimeter. For the weight load that we use for steel is 0, 5, 10, 50, 20, and 25. Why we use the nylon just now is 2, 10, 50 smaller is because it have the smaller range that we use because it's more fragile than steel. So for this week, we need to calculate the reading of twist angle for different length, which is we use the 50 and 30 centimeter. From that we get the data, and after that we calculate the torque for different length, 50 centimeter and 30 centimeter. So which is we calculate all the data, we do the graph. Same just now, we use the twist of angle in degree against the torque in unit Newton millimeter. So from that you can see the trend line. We get the value of slope is equals to 0.0059 for the length 30 centimeter, and for the 50 centimeter is equal to 0.0027. Okay, next is show the last type rod that we use is the aluminium rod. So the aluminium rod diameter is 6.32 millimeter and the C is equals to 3.16 millimeter. So the weight load in Newton that we use is 0, 5, 10, 50, 20 and 25 Newton. So from that we read the twist of angle for all the load and for the different length, which is 50 centimeter and 30 centimeter. For this aluminium, we calculate the value of torque for different length, and after that we do the graph, which is same twist of angle is against the torque. So for the length 30 centimeter, we get the value of the slope 0.0059, and for 50 centimeter we get 0.0035 slope value. After that, we do the calculation part for all the three type of load that we have the data and the graph before. From the graph 1, we calculate the modulus of rigidity of nylon rod. So we have the slope value, which is for 50 centimeter and 30 centimeter, like I have mentioned before. So after that, we calculate the moment of inertia for the nylon rod by using the C that I calculate before, which is equals to moment of inertia equals to pi of, divided to 2 times with 3.31 to the power of 4. So I get the moment of inertia equals to 188.552 millimeter to the power of 4. From that, we calculate the modulus of rigidity for nylon rod by using the formula that I have mentioned before. So for the length 50 centimeter, we get the modulus of rigidity is equals to 73,636, and for the length 30 centimeter, we get 74,907. From that for that two length, we calculate the modulus of rigidity average, which is we plus both and we divide it into 2, so we get it 74,271.5. After that, we use the same step for the steel rod. From the graph 2, we got the slope value, which is for 50 centimeter and 30 centimeter, and after that we calculate the moment of inertia. That for steel rod we get 66.417 millimeter to the power of 4. After that, we calculate the modulus of rigidity for 50 centimeter. We get 21,932.22, and for the length 30 centimeter, we get 95,851.93. After that, we calculate the average. We plus both of them and divide it to 2, we get 58,892.075 Newton meter to the power of negative 2. Next is the last step for result and calculation for this experiment is to calculate the modulus of rigidity for aluminium rod. From the graph 3, we got the slope value for the aluminium rod, like I have mentioned before. So after that, we calculate the moment of inertia for aluminium rod, which is equals to 156.628 millimeter to the power of 4. And we calculate the modulus of rigidity for 50 centimeter. We get 9300.204, and the length 30 centimeter we get 31,354.974. And after that, we calculate the average modulus of rigidity for aluminium rod. We get 20,327.589. That's all from me. Thank you.
For the discussion, to what extent does the experiment verify the twist formula based on the graph plotted angle of the twist against the throat? Based on the three graph plotted, we can calculate that the angle of the twist is directly proportional to the throat. As the throat increase, the angle of the twist also increase. The length of the rod or the material will affect the slope of the graph. As we can see in graph 1 and graph 3, when the length is the decrease, it will cause the slope to be steeper. The graph also shows that the type of materials will affect the angle of the twisting, and except their purely elastic behavior. From the graph, the modulus of rigidity is inversely proportional to angle of the twist. Uh, a smaller angle of twist causing the value of modulus of rigidity increase. Hence, we can calculate that by using this formula. The angle of the twist is directly proportional to the torque. The angle of the twist proportional to the length. The angle of the twist and the angle of the twist inversely proportional to modulus of rigidity. So therefore, we got a formula to calculate the modulus of rigidity G when the angle of the twist equal to TL over JG. Number 2, determine the modulus of rigidity G of the materials from the result and the calculation. The experimental value for the nylon 74271.5, for the steel 58,892.075, for the aluminium 20,327.589. And to calculate the prestige error, we use this formula. Prestige of error equal to experimental minus theoretical over theoretical value and times with 100%. The percentage error for the nylon 0.97, for the steel 25.45, for the aluminium 22.41. Percentage error is computed by comparing the experimental with the theoretical modulus of the rigidity, G the values of the raw materials, the percentage error of the aluminium rod is 22.41, the steel is 25.42%, and the nylon 0.97%, which are quite huge deviations. From the theoretical values, there are a possibility of errors happen in the process of conducting the experiments, which lead the answer accuracy and preciseness, and the following the experimental errors and ways to reduce them, and discuss the errors. Zero errors due to the fitting fitting an incurred plastic pointer to parallax error while reading the angle twist on the measuring scale. Three incorrect calibration or dimensions of the instruments and apparatus used. Uh, uh, Environmental error such as wind movement and temperature interrupting the experimental process, the precautions, and the angle of the twist, which is to investigate the relationship between torque and the angle of the modulus of rigidity of materials has been achieved. The torque is directly proportional to the angle of the twist of the circular cross-section specimen. The greater the torque applied, the greater the angle of the twist of circular cross-section specimen. The modulus of rigidity of each materials also have been determined in the experiment. The modulus of rigidity for the aluminium and steel are 20,327.589 Newton millimeter square and 58,892.075 Newton millimeter square. With the 22.41 and 25.45 of percentage error each last. For the nylon, it has 74271.5 of modulus of rigidity with 0.97 percent of percentage error. This is all on my part. Thank you so much.